In this video we look at the FP2 work on the sketching of rational functions. The specification makes it clear that really we are concerned with just the sketching of the graphs of a rational function, in particular finding their asymptotes, which may be parallel to the axes or indeed a slant axis. A slant asymptote. The major thing you need to have is a procedure for sketching graphs, which will probably involve finding vertical asymptotes, finding the points where curves meet axes, considering the behaviour of a curve as x tends to plus or minus infinity, and if necessary, considering stationary points. And if we put all of that information together, we should be able to produce a decent sketch curve. In the case of a rational function, y equals p of x divided by q of x, where p and q are both polynomials, the important thing is to notice that first of all, the vertical asymptotes will be caused by places where q of x is equal to 0, and then the other asymptotes are a result of the behaviour as x tends to plus or minus infinity. If the degree of the numerator p of x of the rational function is less than the degree of the denominator of the rational function, then y will tend to 0 as x tends to plus or minus infinity. In other words, the x-axis will be an asymptote of the curve. If the degree of p is the same as the degree of q, then there will be a horizontal asymptote, which can be found by a variety of methods, either by dividing top and bottom of the fraction by x to the n, where n is the degree of the top and the bottom of the rational function, or by a process of polynomial division. If the degree of p is 1 more than the degree of the denominator, then there will be a slant asymptote whose equation can be found using some process of polynomial division. So let's rapidly move on and have a look at some exam examples on sketching rational functions. So for the first one, we have the function f of x is x divided by x minus 1 squared. And the question leads us through the process of producing a sketch graph for the function f of x. So the first thing we've got to do is find the stationary points, so we need to do some differentiation. So we've got f of x is x over x minus 1 squared. So f dash x, well, we'll need to use the quotient rule. So first of all, differentiate the x is 1 times by the bottom, which is x minus 1 squared. Take away x times by the derivative of the bottom, which is 2 lots of x minus 1, divided by the bottom squared. So that's x minus 1 to the power 4. The top has got a common factor of x minus 1. So factorising, we've got x minus 1 times by x minus 1, take away 2x. And at this stage here, we can spot that we've got a factor of x minus 1 here, which will cancel out with one of the factors of x minus 1 here. So we'll end up with just x minus 1 cubed on the denominator. And x minus 1 minus 2x simplifies to just minus 1 minus x. So we've got f dash x is minus 1 minus x over x minus 1 cubed. We're looking for the stationary points, So we want f dash x to equal 0. So that means that minus 1 minus x must equal 0. In other words, x must be minus 1. And if x is minus 1, going back to the rule here, we've got f of x is going to be minus 1 divided by negative 2 squared. So that's minus 1 divided by 4 minus a quarter. So we've got the stationary point is minus 1 minus a quarter. So it now wants to know the equation of each of the asymptotes of the graph of f. So first of all, we notice we've got a denominator of x minus 1 squared, which means that we're going to be dividing by 0 when x equals 1. So we're going to have a vertical asymptote at x equals 1. So straight away we'll put that onto our axes. So there we are, we have a vertical asymptote at x equals 1. If x is a little bit bigger than 1, then f of x is 1 divided by a very small positive number squared. So if x is a little bit bigger than 1, f of x is going to be a large positive number. So as x gets closer and closer to 1 from above, the value of y is going to get larger and larger. If x is just a little bit less than 1, again we have here a number which is roughly 1. X minus 1 is going to be a small negative number. Square that, we get a very small positive number. So we've got something which is roughly 1 divided by a very small positive number. So again, the value of y is going to be very large and positive. It's worth noticing, as part of our process, we're going to have to think about what happens where the graph crosses the axes. And a moment or two's thought tells you the only point where the graph crosses the axes is going to be when x equals 0, y is 0. So think now about the second asymptote. What we have here is we have a linear function, x, divided by a quadratic function, x squared, or x minus 1 squared. As x gets very, very large, x over x minus 1 squared is going to get very, very small, because the degree of the top is smaller than the degree of the bottom. So as x tends to infinity, y is certainly going to tend to 0. So we have a horizontal asymptote of y equals 0, in other words the x-axis. If x is a very large positive number, x over x minus 1 squared is going to be a small positive number. So we're going to be approaching the x-axis from above. On the other hand, if x is a very large negative number, then x over x minus 1 squared is going to be a large negative number divided by a very large positive number. So that's going to give me a small negative number. So there we go. So we've got both the equations of both of the asymptotes. We've seen that we have a stationary point at the point minus 1 minus a quarter, which will be put onto the sketch graph. And now putting all of the information together, we can finish the sketch off. So there is our sketch of the graph of f of x. Finally, we have to find the inverse of under f of the interval 0, 2. We've got to find f to the minus 1 of a, where a is 0, 2. So there's our graph. The interval 0, 2 on the y-axis is there. So we got y equals 2 going across. We need to find out what the corresponding x values are. So f of x equals 2. We've got x equals x over x minus 1 squared equals 2. So that's x equals 2x squared minus 4x plus 2. So simple quadratic to solve, which leads us to x equals a half or x equals 2. So the first set of values of x, which give us a value of f of x, which lies between 0 and 2, are going to be values of x which lie between 0 and a half. The second set of values that lead to a value of f of x that lies between 0 and 2 are going to come from values of x which lie between 2 and infinity. So we have f to the minus 1 of a is the interval 0 to half combined with the interval 2 to infinity. So a look at the mark scheme shows that for part A there are 2 marks for using the quotient rule to find f dash x, and then another 2 marks for finding the position of the stationary point. There are 2 marks for part B for finding the equation of each of the 2 asymptotes of the graph. Sketching the graph then from the information that was given gave 2 marks, and then to find f to the minus 1 of a there were 3 marks for obtaining the 2 values where f of x had to equal 2, and then 2 more answer marks for correctly obtaining f to the minus 1 of a. So let us now move and look at a second example which comes from the 2011 paper. We have f of x is x plus 1 all squared divided by x minus 1 times x minus 2. We have to prove that f of x can be written in an alternative form. There's a couple of permissible ways of doing this. One would be to use some polynomial division and partial fractions work. Rather easier though is simply to start with the final expression here and prove that that can be rewritten as f of x. So we have a 3-term expression with 3 terms being added and subtracted. 2 of the terms are fractions, so we'll certainly need to use a common denominator, which will be x minus 1 times x minus 2. The 1 will become x minus 1, x minus 2 over x minus 1, x minus 2. The 4 over x minus 1 becomes 4 lots of x minus 2 over x minus 1, x minus 2. And the 9 over x minus 2 will become 9 lots of x minus 1 over x minus 1, x minus 2. Expanding the brackets on the numerator gives me that, and then simplifying gives me x squared plus 2x plus 1 over x minus 1, x minus 2, or x plus 1 squared over x minus 1, x minus 2, which is f of x. So we know that f of x can be written as 1 minus 4 over x minus 1 plus 9 over x minus 2, which of course we can rewrite as 1 minus 4 lots of x minus 1 to the minus 1, add 9 lots of x minus 2 to the minus 1. Using the chain rule, we can now find that f dash x is 4 lots of x minus 1 to the minus 2, take away 9 lots of x minus 2 to the minus 2, and that the second derivative of f is minus 8 lots of x minus 1 to the minus 3, add 18 lots of x minus 2 to the minus 3. And again, that was obtained just using the chain rule. So there are our expressions for f dash x and f, the second derivative of f. So we now want to find the stationary points and classify them. So for a stationary point, we must have f dash x equals 0. So that's 4 over x minus 1 squared. Take away 9 over x minus 2 squared must equal 0. Multiply through by x minus 1 squared, x minus 2 squared. To obtain 4 lots of x minus 2 squared, take away 9 lots of x minus 1 squared must equal 0. Expand and simplify and solve the quadratic equation to find that x is either minus 1 or 7 over 5. If x is minus 1, then we have f of x is going to be 0. The second derivative when x is minus 1 is positive, so we obtain a minimum at minus 1, 0. On the other hand, if x is 7 over 5, then we have f of 1.4, or 7 over 5, is minus 24. The second derivative of 1.4 is a negative number, which means we have got a maximum at the point 1.4 minus 24. Now we now need to find the equation of each of the asymptotes on the graph. Well, first of all, we've got asymptotes wherever the denominator is equal to 0. So we are going to have vertical asymptotes at x equals 1 and x equals 2. The alternative form that we have here makes the behaviour as x tends to plus infinity or minus infinity very, very clear. As x tends to plus infinity, this gets closer and closer to 0, and this also gets closer and closer to 0. So we're going to have a horizontal asymptote at y equals 1. So finally, we've now got to try and draw the graph of f of x. So there are my axes. So we'll first of all put on the vertical asymptotes, which is at x equals 1 and x equals 2. If the value of x is a little bit bigger than 2, then the top is roughly 9. This term here is roughly 1. This term here will be a very small positive number, so I've got 9 divided by a small positive number, and that's going to give me a very large positive number. So the graph is going to shoot off in the positive direction as x gets closer and closer to 2 from above. On the other hand, if x is just a little bit less than 2, then the top here is still roughly 9. X minus 1 is still going to be roughly 1, but x take away 2 now is going to be a small negative number. So what I've got, roughly speaking, is 9 divided by a very small negative number, and that's going to give me a very large negative number. So the graph is going to be shooting off in the negative direction. If we move to x being just a little bit more than 1, then x plus 1 squared is going to be just a little bit more than 4. X take away 1 is going to be a small positive number. X take away 2 is going to be roughly minus 1. So I'm going to have 4 divided by a small negative number, so that's going to give me a very large negative number. And finally, if x is just a little bit less than 1, the top is still going to be roughly 4. X minus 1 is going to be a negative number, but a very small negative number. And x minus 2 is going to be roughly minus 1. So the bottom is going to be a very small positive number. So I've got 4 divided by a very small positive number, which is going to give me a very large positive number. We need to have a think about where the curve crosses the axes. Well, if x is 0, we have got y equals 1 over 2. So the graph goes through the point 0, 1/2. If y equals 0, then the numerator of the rational function must be 0. So that means that x must be equal to minus 1. Now, we know that we have a horizontal asymptote at y equals 1. If x is a very large positive number, then we've got 1, take away 4 over x minus 1, plus 9 over x minus 2. Now, if we think about, let's say, x equals 100, we've got minus 4 over 99, plus 9 over 98, and it's fairly clear that the 9 over 98 will be slightly bigger than the 4 over 99. In other words, these two terms together are going to give us a small positive number, which means that we will be approaching y equals 1 from above. Similarly, if we have x is minus 100, then we're going to have minus 4 over minus 101. So that's plus 4 over 101. And then we're going to have 9 over minus 102. So we're going to have 4 over 101, take away 9 over 102, which is going to give us a negative. So we're going to be approaching y equals 1 from below. We need to mark in the stationary points that we found. So there, the maximum and the minimum point that we've got. And we can then join the information up to obtain our final sketch curve. Okay, so the marking for this example, there were 4 marks for moving from the original expression for f of x through to the alternative form, or vice versa. 2 marks for the first derivative and 1 additional mark for the second derivative. For the stationary points, there are 2 marks for obtaining the equation f-x equals 0, and then 2 marks for finding the first stationary point and classifying it, and another 2 marks for finding the second stationary point and classifying it. 2 answer marks for the asymptotes, and then the sketch graph gave us 3 marks at the end of the question. So let's now move on to our final question, which comes from the 2008 paper. And in this case, we are looking at the function f of x is x times by x plus 3 divided by x minus 1. So the first bit says we've got to show that f of x can be rewritten in the form ax plus b plus c over x minus 1, where a, b and c are constants to be found. Well, we've got a quadratic expression divided by a linear expression. And if we divide a quadratic by a linear, then we know that the quotient term will be a linear expression, and that the remainder will simply be a constant. So we can certainly say that f of x, or x times x plus 3 divided by x minus 1, will be our linear term, ax plus b, plus our constant remainder, c, divided by x minus 1. If we multiply that up by x minus 1, we obtain x times x plus 3 must equal ax plus b times x minus 1 plus c. And then if we put x equals 1, the left-hand side is simply 1 times 4, which is 4. The right-hand side is 0, add c, so that we know that 4 must be the value of c. If we now put x equals 0 in, we've got 0 on the left-hand side is b times minus 1, add c, so we've got negative b plus c must equal 0. We know that c is 4, so therefore b must be equal to 4. And finally, if we look at the x squared terms, we've got 1x squared in the expansion of the left-hand side. We've got a lots of x squared on the expansion of the right-hand side. So we know that a must equal 1. So we know that f of x must be the same thing as x plus 4 over x minus 1. We've now got to find the stationary points of the graph of f. So, remembering that we already know that f of x is x plus 4 lots of x minus 1 to the minus 1. Then we know that f dash x is 1, take away 4 lots of x minus 1 to the minus 2. And we need that to equal 0 for a stationary point. So we've got 1, take away 4 over x minus 1 squared must equal 0. In other words, x minus 1 squared must be equal to 4. That means that x minus 1 has either got to be 2 or minus 2. So x must either be 3 or minus 1. If we work out f of 3, we've got f of 3 is 3 times 6, which is 18, divided by 2, which is 9. If we work out f of minus 1, we've got minus 1 times 2, divided by minus 2, which gives me 1. So we have stationary points of 3, 9 and minus 1, 1. So, we've got to state the equation of the asymptotes and sketch the graph. Well, first of all, looking at this, we can see that the denominator of the fraction will equal 0 when x equals 1. So we'll mark this vertical asymptote in on our sketch graph straight away. Now, if x is a little bit bigger than 1, then x times x plus 3 is roughly 4, divided by a very small positive number. So the value of f of x is going to be very large and positive. If x is just a little bit less than 1, the top is still roughly 4, the bottom has become a very small negative number. 4 divided by a very small negative number is going to give me a very large negative number. Now, if x is very, very large, the 4 over x minus 1 term here is negligible. So f of x is going to be very close to the value of x plus 4, which means that we have got a slant asymptote of y equals x plus 4. So there's the slant asymptote gone in. If we just stop and think about it, if x is a very large positive number, 4 over x minus 1 is going to be a very small positive number, so the value of f of x is going to be just a little bit more than the value of x plus 4. On the other hand, if x is a very large negative number, 4 over x minus 1 is going to be a negative number, so the value of f of x is going to be just a little bit less than the value of x plus 4. We need to have a think about where the curve crosses the axes. So when x is 0, we have got f of 0, we've got y is 0 because f of 0 is 0. And when y is 0, then the numerator must be 0. In other words, x must be 0 or minus 3. So we'll put those in on our sketch. Put the maximum and minimum points, or the stationary points, in on our sketch, and then finally join all the information up to produce the final sketch. Okay, so the marks for this, well, the first 3 marks would be for obtaining the alternative expression x plus 4 plus 4 over x minus 1 for f of x. Then we had the differentiation and solving the consequent f dash x equals 0 equation to find the stationary points gives us 4 marks. 1 mark for each of the 2 asymptotes, and then 2 marks for producing the final sketch.